Welcome, and thank you for joining us for what is our second to last lecture. We're off next week for Thanksgiving. There is no lecture on next Saturday, and you all should have seen that there's a sign-up sheet for the lunch that was with today's handout. So if you want to fill that out and send it out, I think there's instructions on the form on how to do that. The talk that I want to give today is about impact and what the effect is of things, large objects, hundreds of kilometer-sized objects hitting the planet, and those will have obviously dramatic effects, right? We've talked about how something very large hitting the planet gave us the moon, put part of the Earth into outer space. They can destroy things, right? About a 10-kilometer diameter impactor is what killed off the dinosaurs, so that's pretty small, and that had the massive global consequences. So today's talk is a revised version of a talk that I've given about my own research, and I've left the cover slide alone because I really like this picture. This is from one of the Apollo missions. This is a picture of you're orbiting over the moon of the Earth. This is the sort of the Earthrise picture. So impacts have been studied for a long time. They're one of the most exciting geologic phenomena, right? We've talked about things happening here on a time scale of millions of years or billions of years, and impacts are things that happen in an instant. These are things that happen in time scales of seconds, hours, days. And so in a review paper, the question really is how high was the impact rate in the early Earth? Because impacts can be both beneficial and they can be disruptive. So in this figure here, what you can see is this is present day, and this is the time in billions of years before present. And this is just a sort of a guess at how much energy you're getting into the planet for an impact. The KT boundary here at the bottom, first I want to note this is a sort of a log scale, so this is a factor of, actually it's every time you go from here to here, this is a factor of 100 times energy. So the KT boundary impactor, the thing that killed all the dinosaurs, is actually pretty small. If we go look back at some of the early craters on Earth, Sudbury, Redford, these are 2 billion-year-old craters in Canada and South Africa. So they're sort of, at least an order of magnitude bigger. Imbrium, Orientalis, these are on the moon. And then these are sort of hypothesized to take place. But now, if you're looking at this and going, well, I don't actually have a good feeling for what 10 to the 23 joules is, I looked at some comparisons, and I'm just going to cheat and use my phone so that I don't lie to you about what the numbers are. Let's see. All nuclear fission explosions, so every atomic bomb we've ever exploded would be 10 to the 15, so it would plot somewhere down here. The Tsar bomb is 10 to the 17. A large earthquake is about 10 to the 18, so still not plotting here. And the only thing that I actually found that plots anywhere close to this scale, to give you a magnitude of how much energy this is the annual energy consumption for humans on this planet is about 10 to the 21 joules. So all of the energy that we use in a year barely gets us to the bottom of the graph. So these could clearly be disruptive. And the other part is that, here is our calculations for how much energy it would take to boil off all of the, to boil off this much water, to boil off 30 meters of water globally. And this is basically, this would be boiling off the Earth's ocean. And so one of the points is if the impact rates are sufficiently high, you're just going to continuously boil off the oceans because the planet's going to be so hot. On the other hand, in a really nice study from 2009, to get to the less destructive, possibly beneficial end, Abramov and Moisich did thermal calculations and said, well, if we use the impact rate that we think we have from the moon, which is what we're going to spend a lot of time on today for this time period, then actually this is the lithospheric fraction. So this, just want you to think of, this is how much of the crust gets heated up by this temperature. So here's 20% of the crust, 40, 60, 80. And their point actually is that while there are dramatic effects where you have, 1,000-degree temperature increases, actually for most of the crust, for at least half of it, you're seeing maybe a 20 or 30 degree increase on average. So that would take you, from frozen water to a warm, from winter to a warm summer day for most of the crust. And that this could actually be beneficial because things like hyperthermophiles, which live in hydrothermal systems, these are bacteria that like the heat, they would actually love this kind of an environment. So maybe impacts can bring in material, but maybe they can also heat stuff up and help the development of life. So we can get both ends of the extreme. If we don't know what the rates are, we can blow everything away on the planet, or maybe it's beneficial. So the sort of standard models of planet formation that we talked about, small dust particles accreting into meter-sized particles, into tens of meters, hundreds of meters, kilometer-sized objects, would suggest that in the early solar system there's a lot of junk flying around that could potentially hit your planet. So we think this was high. We have evidence for this just by looking at the moon, right? There's an impact basin, there's an impact basin, there's an impact basin. Basically, any of the black dots that you see on the moon are sort of 1,000-kilometer-sized impact basins. And what happened is that the white stuff here is the original crust of the moon. These are the Corona and orthosites. These formed early, and these are impacts that punctured through this, melted the mantle, and then they solidified, and that's why they have a different colors. And one of the sort of big concepts that has come out of this that I want to spend a lot of time on, that has been a lot of my career, is there's a notion that at 3.9 billion years ago, there was a peak in impacts called the late heavy bombardment. This comes about to us from Apollo samples, and really we understand this mostly in context of looking at the moon. So because we don't have old crust, right, we don't preserve old impact craters, we have two that are like 2 billion years old, we have no impact craters that are older than this, we have no way of estimating this record from the Earth, we have to go look at the moon in order to understand this, because the moon preserves this old surface, because it doesn't have water on it, it doesn't have the erosive processes, it doesn't have plate tectonics that continuously resurface it. So the moon is this benchmark. We're basically using it as, it's the thing that was sort of flying around the Earth and was sort of catching impact, sampling sort of the same population. Some impactors hit here, maybe 20 times more hit the Earth, depending on how you want to scale between them. So where does this late heavy bombardment as a concept come from? When they started getting Apollo samples back, they used a lot of decay systems, radiometric dating. We've talked about uranium-lead dating, where uranium decays to lead. And they used something called potassium-argon, where potassium-40 decays to argon-40. And you can date it because rocks don't really form with argon in them. They form with a lot of potassium, though. And rubidium strontium works the same way. 87 rubidium decays to 87 strontium. We've also seen this used in this lecture. And they said, look, if we look at this, there's an awful lot. Right here's 3.8 billion years, here's 4 billion years. This AE just means billions of years for our purposes. So 3.8 to 4 billion years, we're saying, look, there's a lot of ages here. So clearly some traumatic event happened on the moon at about 3.9 billion years, and this was argued to be a spike in impacts. That the moon is basically geologically dead at this time period, and it's already pretty cool, so you don't have volcanoes sort of popping off at this time is the argument. And then you see all of these ages, so how do you make molten rock on a dead body? Well, you slam impactors into it. So this was proposed based off just sort of a collection of ages until about 2005, when Gomes et al. Wrote a paper saying that Jupiter and Saturn rearranged in their orbit early in the solar system's history, and that this destabilized the main asteroid belt, the comets, and that this is what provided the impact flux into the Earth-Moon system. And this was called the Nice model, which is a kind of terrible thing to Google to get pictures of. You end up with something completely different. And, right, just to show you, here's another compilation. Here's lunar rock resetting. These are the ages. And again, you get a spike at sort of 3.9 billion years, and you get not very little before, very little after. So let's talk about the Nice model. So this is now the time. The axis is the same for both plots. And they're saying, here's 200 million years, 400, here's about 1 billion years after. So this particular model run actually caused it a little late, 4.5 billion year old, 3.9. You need about 700 million years, so you'd like it here, but the model predicted here. So what these codes do is they simulate the solar system. So you put in your planets, you put in your sort of disk of stuff in the asteroid belt and the Kuiper belt, and then you let it run for hundreds of millions of years, and you see what happens. And their claim is that here are plots of one of these is Jupiter, one of these is Saturn. They're kind of stable. These are basically the closest point and the furthest point in the orbit for each, so for the black and the gray. So they get close, they get far, and kind of nothing happens. There's a little bit of drift, and boom. There's a huge event. You're getting orbits that are really, really, really messed up, right? Look at how close this gets versus how far away this is. And what you see, this is cumulative lunar impact mass. So this is the mass in grams that's hitting. And what you get is, so for the first part, look, you're getting a little bit of mass gently through comets, but not much really. And then when this flipping in the orbits has, you're destabilizing the asteroid belt, and that massively adds to your flux and impact. And you can naturally produce this impact spike. So that's great. As of 2005, we not only have evidence, but we have a model. And now if this works, this is a movie made by Alessandro Morbidelli that sort of shows you what's happening. The movie's kind of fast, so we might have to watch it twice. So here are 4 of the orbits of the planets. Here, this is actually the Kuiper belt way out. This is AU, so the Earth isn't really visible here. These are the gas giants, basically. And so here's the time coming up to 500 million years. Nothing's happening, and I want you to watch. These are the planetary orbits. They're going to do something crazy soon. And basically, there you go. We have now scattered stuff around, and in this event, in the planets moving, watch it again just because of how dramatic it is, you end up scattering these green planetesimal, these impactors, and these can hit the moon, these can hit the Earth, and these can give you that spike in impact at 3.9 billion years. The problem with these simulations is that they also tend to eject the Earth from the solar system, which I view as a minor flaw in that we're standing here today, still in the solar system. So people have proposed various solutions to that particular problem, essentially by making that jump happen really, 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 really quickly. So the faster that Jupiter and Saturn switch in their orbit, the more likely the Earth is to remain in the solar system. So, but let's go back and actually look at the constraint for these types of simulations. I've shown you these sort of histograms with the spikes. But I actually want to discuss the chronology of this a little bit because it's what I spent my PhD working on. And I actually want to sort of look at how the timing is constrained. So the 2 constraints that have become really popular over time are the magnitude. This comes to us from highly siderophile elements. We've talked about these early on in like core formation for the Earth. So this is your stuff like platinum and gold. The idea is that early on the core would strip all of those out. And whatever excess you have is a way to record how much extraterrestrial material that was added because the core is so efficient at removing this. On the moon, this is argued to be about 10 to the 19 kilograms per 100 impactors. So let's not actually worry too much about this. This is true with an impactor too, but it's not really the point I want to make. The thing that I want to actually get at is the timing. So the system that is used to do this is potassium-argon dating. It slightly is a variant, so potassium decays to argon. But when you look at, here I plot, this is a probability, so this is one of these histograms, sort of added up and compiled together. Here are meteorites from Vesta, here are some chondritic meteorites, here are the Apollo 16 samples, and they look pretty similar to all of the Apollo samples. And here is that great spike at, somewhere around 3.9 billion years that I showed you before, right? Well, the first problem with this is that the lunar meteorites, which are meteorites that were kicked off the surface of the moon and collected here, don't actually show a spike at 3.9 billion years. So the moon appears to disagree with itself. If you look at the Apollo samples, you get this clear spike, But the lunar meteorites are this random sample of the moon, right? For the Apollo mission, we went to the near side of the moon. They were all kind of close to each other. We basically sampled the same spot on the moon over and over again. The lunar meteorites could have been picked off from anywhere, so they should be a sort of a random sampling of the moon, and they don't show us this spike. So what's going on here? If we have this massive impact event, how come only a tiny portion of the moon saw it? And could this maybe be a local event? Or could there be some issues in the chronology? This is again sort of the billion years as determined by this system, that there's maybe an issue here in how these ages were derived. So to sort of zoom out a little bit, it is of course possible that the 3.9 event, if it sort of exists, is actually just a little bit of an accident. There's actually, it's hard, because of how many events are here, how many rock ages are here at 3.9, to study this early history. So that spike idea is what's called a single cataclysm. But maybe it was just a smooth decline and it was overprinting itself, and that's all we can see is that last sort of 3.9, because that's when the impact rate was low enough to not actually saturate the moon, right? If I'm continuously bombarding the moon with impact, maybe the rate at 4 billion years is so high that at 3.9 billion years, I've destroyed everything again. So if I continuously destroy everything, I keep erasing older evidence. So maybe that there were multiple cataclysms, maybe this was a single spike. So this is sort of the state of the art as of 2007. Anyway, the dynamical modelers actually got together. Here's Morbidelli again, one of these. And he proposed that this timing at 3.9 for the event is problematic, and he didn't like it very much. And so this is now, this plot is the cumulative number of craters that are greater than 1 kilometer per square kilometer. So there's basically, 0.1 craters per, so basically 10% is covered by 1 kilometer bigger craters on a surface that is 4 billion years old on the moon. And what Morbidelli said is, well, if I smoothly extrapolate this back to when the moon formed, I add way too much of these highly siderophile elements to the moon that this is not really plausible. So he proposed, we've now switched to a number greater than 20 kilometers, but sort of same thing. This is the number of craters. And he proposed, cumulative number, and he proposed that there be a bombardment episode like this late heavy bombardment, like this spike at 3.9 billion years, but he wanted to move it in 2012 to 4.1 billion years and said that he kind of liked it better from the extrapolation point of view. So there it is. So now we've moved, I know the plot doesn't look super dramatic, but now we've moved this massive cataclysm. The planets are moving in their orbits, not at 3.9, but at 4.1 billion years. So the implications of this bombardment were really nicely worked out in a paper that we saw briefly by Markey et al. In 2014. And this bombardment would have been immense. You're talking about covering 600% of the surface area of the Earth during this time period in 3 kilometer thick impact melt. So you're covering the planet 6 times over in impact melt. So you're continuously destroying the upper surface, the outer part of the planet during this time period. And they would destroy the crust, the melt, the upper mantle. The record that we have from this time period, the Hadean zircons, could not have possibly survived this. And actually he argues that it created them, but for geochemical reasons that's pretty much out, because this is a really dry process. Liquid water is not really stable in these conditions, and we know we need a lot of liquid water to make the Hadean zircons. So this was proposed, and basically left me with the question, well, if the lunar impact record is telling us that this time period was so insane with impact that you're destroying the entire planet over and over again, and the Earth is telling us, really, it was quite nice out. There was liquid water. There may have been plate tectonics. There may have been life back then. So how do you reconcile these two records with each other? And where is the problem? What is causing this massive difference between these two records? So I wanted to look at the dating. So the two questions that I sort of want to pose is, first off, can we turn an age compilation? I showed you these histograms of ages, and my question is very simple. Can we actually use that to infer an impact record? Or is that misleading? And there's many different ways to do this. And then, do we actually sort of require this? Is there any geochemical evidence, these highly siderophile evidence? I don't know quite if we'll get to this today, but certainly this is the important part that I want to go with. Basically, do we have evidence that requires this, or are the error bars such that we can get away with quite low impact rates early on in the planet's history? So how is argon, so potassium decays to argon. It's got a half-life of about 1.25 billion years. So the GA here stands for giga-annum, annum being Latin for year. So that's 1.25 billion years. But measuring the concentration of potassium and argon in the exact same sample is really hard. Argon is a gas that doesn't like to react. Potassium is a very volatile reactive solid. Actually doing that analysis in the same instrument is incredibly difficult, and the thing is you can't actually do it. So, back maybe 40 years ago, somebody figured out, well, potassium has two isotopes. 39, sorry, actually has three. 39, however, turns into 39 argon if you stick it in a nuclear reactor and shoot neutrons at it. Well, that's great, because now we can simply measure how much argon 40 there is from the decay of potassium 40 to how much 39 argon we produce in a nuclear reactor, and that way we can get our age. So the argon 40 to 39 ratio after we stick it in a nuclear reactor is proportional to the age of the sample. So that's easy. Now we just have to measure argon. There's a nice picture of the Cherenkov radiation from one of these reactors. Here actually is a picture of the argon lab in which I took some of my own analyses. Back there is a mass spectrometer, lots of computer monitors, lasers to heat the sample and get the gas out. So what is done in these analyses is really very simple. You take your rock, you drop it in a furnace, you heat it up for, let's say, to 400 degrees for 10 minutes, and then you look at how much argon came out and what its age is, right? So we just measure, we just count how much argon 40 there is relative to argon 39, and then we can make these great plots. Because then we can take the sample and heat it again, maybe to 450 degrees for 10 minutes, until the sample doesn't have any argon left in it. So we can do this over and over again. Because it's in a furnace, we can control the temperature to which we heat it to how long. And so what we get is a plot of age. So each of these is one heating step that was analyzed for the gas. And then basically we keep doing this. And look, in this sample, we get the same age over and over and over again. And then this is the age of the rock. Because there's no evidence for disturbance here. So basically the first gas that came out here to the last argon that came out, this, the way I want you to think of this is that the first argon that comes out is the least retentive argon. It's the easiest. It wants to leave. It's like the people sitting by the door. They're the first out of the room, right? If we make it uncomfortably hot in here, the people in the back are the first people out of the room, and the people up front here are the last people out of the room, and they're the most retentive. So this gives us some sense of how the age behaves as we heat the rock and how simple its history was. Well, unfortunately, Apollo samples don't look like the idealized case I just showed you. What you can see here, so this is age of the heating step, and I hope everyone can see it. This is 1.6 billion years, 1,600 million years, going all the way up to about 3.8 billion years, or 3,800 million years. So there's the 2 billion year age gradient from the first gas that came out to the last gas that came out. And the question is, how do you then assign an age to a sample that gives you a 2 billion year age gradient? What is traditionally done is that people say, well, I have absolutely no idea what happened in this first part, but that looks to be quite reproducible, so I'm just going to take that age. The original paper that actually discusses this technique and does this actually says, we're only talking about these cases. We have no idea what to do in these cases. That's actually the last sentence of the paper is, it's unknown what you should do in these cases. Well, the community has decided in the meantime to simply say, well, this is the right age. The problem is, and I want to sort of, we'll just stick up to this, the early case, when I sort of gave you the example of the people who are the most likely to leave the room if I repeat the temperature, right, in the back are the ones that can get out. The gas that is close to the edge of a mineral in a rock is like the people in the back of the room. If I heat it up, they're the first ones to leave. So if the rock is sitting out in nature, the argon-40 is going to want to diffuse out of the rock, and it's going to want to leave if the rock gets warm. So this is driven basically by a distance from the boundary. So the easiest gas to leave is the gas that is closest to the grain boundary. It's close to the edge of the mineral. It's like the people in the back of the room. They get to leave first. The people in the front of the room are kind of stuck until that gets cleared out. The thing that tends to happen if you simulate this process, however, is this is a very simple numerical model that says the age of this rock was 1.0 all the way across, and 0, which is present day, I heated it in my computer. It's just a computer model, just to give you a feel. 10, 30, 60% of the gas. And then we run a sort of fake argon analysis on this. And what we get is there's always flat sections. But look, this is giving me an age that is under 0.5 when it should have been 1. So what this is saying is that in these nice cases where even if you get this flat behavior, you can get the wrong age. You can completely get the wrong age. Here we're off by a factor of 2 at 60% loss. But even at 10% loss, we're off by a couple of percent. Well, a couple of percent in a 4 billion year sample is actually quite a significant amount of time. So the point is, this flat behavior, this flat portion of the age spectrum, is not a good indication that your age is reliable. It is an actual feature of diffusion. So this is not actually the age of the sample. Just to give you some more examples, here's one where it never actually got flat. They just said that was the age. So we can do this, and what I set up as a model that I just want to run through as a sort of the simplest way that I think I can explain this, so we'll see if it works. If not, it's my fault. Is that what I want you to look at is, again, this is the same example as I calculated previously, but that the age of the gas that is early comes out very close to when I said you should lose your gas. So that first little bit of gas, the argon atoms sitting really close to the boundary of the mineral, are gone if you look at them fine. They're gone really easily, so that tells you the last time this sample was warmed. So basically, what I did is I compiled up these ages and said, well, you're telling me the last time that my sample was heated on the surface of the moon. So we can get a totally different chronology and try to see what influences this has back here. Because again, these are samples that formed at the same time. This one was heated more, and therefore would give you a lower age because it experienced more heating. So we can do this just to put some real numbers on it. Same model, 10 to 95% loss in an event at about 2.2 billion years ago for a sample that is originally 4.57 billion years old. So basically, the sample as old as the solar system loses some of that argon that it got from radioactive decay, and at 60% loss, you're getting an age of about 3.7. So you've lost, just under 1 billion years off the right age of the sample. So taking this flat portion, which people do very commonly and saying, this is the age of my sample, is only a lower limit. It does not actually tell you the age of your sample. So we'll look at these. So basically what I went through and meticulously compiled up is these ages here, the ages of this first least retentive gas, and said, well, what does that look like? Well, it looks to be sort of monotonically declining. Here's my histogram of these ages. It starts at about 4 billion years, and then it just kind of gets younger. So we're not retaining any of this information in older samples, but it just seems to monotonically drop off. It does not give any great evidence for a tremendous spike at 3.9 billion years. And, well, this is now what I now want to do, and what the text on this slide simply says is that I want to take a lunar surface. I'm going to make a lunar surface. I'm going to give it an age, and I'm going to say, the rocks are this old, and I'm just going to forward simulate an impact history. So I'm going to say an impact hits at this time, it heats up this much of the rocks, and they lose this much of the argon, and I'm going to constrain it to the plot on the previous slide that I showed you, these intercept ages. And I'm just going to see what I can do with that. Well, we need an age for the lunar surface, so I used zircon ages. This is really not that important. So basically I said, you know, the lunar surface has this kind of an initial age distribution. And we can look at this, and then basically what this model does is it says, you know, some portion of the lunar surface crystallized at this point, and it's going to get randomly hit by impacts. I'm going to tell it how many times it gets hit by impact, how much argon you lose. We can simulate that, we can make good guesses at that, and the question I want to have is, will I get a spike in impact ages or not? So the first thing I did is I said, I'm not giving you really any sort of constraints. I'm just going to run it and just tie you to this sort of those intercept ages, those last times the samples was heated, this monotonically decreasing from that. And what I want to show you is that when you do this and say that you have some probability of losing your argon, so you lose some argon in each impact, what you get, quite simply, is something that looks an awful lot like the lunar meteorite spectrum, right? So here you have this broad feature between 3 and 4 billion years. Well, that's great. The model makes a broad feature between 3 and 4 billion years. The important thing that I want to point out here is I didn't tell it to put in an impact spike. The impact flux is continuously decreasing while this model is running. So you can get apparent spikes in your age compilation from a monotonically declining impact history. And the follow-up to that is that I then said, well, I'm not necessarily super thrilled by my spike. Can I make my spike spikier at 3.9 billion years? I really want to make a sharp feature. What knobs do I have to turn to do this? Can I do this in a way that is sort of simple? And the answer is yes. I need to play with how much argon you lose in an impact event. And then, when I make this that you lose sort of very little argon, you can actually make spikes. This is a monotonically decreasing impact history, and what this is a spike that naturally results out of the model. So this is saying that the lunar surface crystallized, you know, 4.3 billion years-ish here, and then there was a sort of exponentially decreasing impact history into this surface, and that gives you a rise to these younger age distributions. So basically, finding a spike in argon ages is not actually evidence that any sort of spike in the impact history happened. Because what is happening is, if you remember, the original distribution for the surface of the moon, right, the age distribution was quite sharp. Most of the lunar surface formed at about the same time, so that already looks like a spike. All that the impact history is doing is moving that spike to younger ages. It is not actually capable of producing one. So, actually, I think for simplicity we're just going to have to skip. This is simply here to convince you that the model is actually quite reasonable, but we're just going to. These are the impact histories. Now this is what I wanted to show you, is that in the two models that themselves show spikes in the argon spectrum, in these histograms, in this compilation, you can make them without invoking any sort of spike in impact. So here is the time, and again in billions of years, present, going back in time. Here's where the late heavy bombardment is happening. This is where this apparent clustering of ages is happening, where people say, oh look, we see this spike in ages, we see this histogram that is peaked there, so there must have been a spike in impact, and the point of this model is simply to show you that with very simple assumptions, to just sort of test this hypothesis, you can get curves. These black and blue curves are the impact histories on a log plot, so normalized to the present day impact flux. So basically it's saying there were 100 times more impact back during this time period. And so you don't actually need a spike in impact to make an apparent spike in these argon ages. So this evidence is very indirect that you're getting. And so you can actually get away with a simple declining history and make evidence that looks the same as what we observe today. So this evidence is not a unique signal. So can we turn argon age compilations into impact rates? And the answer is not uniquely. There could have been a spike, or there may not have been one. The evidence doesn't actually require it because the evidence isn't capable of telling you what this is. So since we have, the next part is, do we, people, right, the original thing for moving this to 4.1 billion years, the observation is that, well, if we just extrapolate it back, we would accrete way too much mass to the moon, is based upon, right, these sort of extrapolations here, but these dots, what they really represent is ages of an impact crater on the surface of the moon that was dated through argon-argon dating, the thing that isn't a really good system to get ages, and then people count how many impacts there are into this well-dated surface so that they can tell you, a 4 billion-year-old surface on the moon caught this many craters per square kilometer, basically. And so as you go back in time, there should be more craters. This is about the oldest plane surface. And then younger surfaces, by 3.5, have caught very little. So this is the cumulative number of craters that are larger than 1 kilometer per square kilometer, and then older surface, because they are been exposed to impact for a longer time, naturally have more impact on them. And so you can make, and then from the number of impacts, there are scaling relationships. It's about 10 to 1 in most cases. So a 10 kilometer impact crater was about a 1 kilometer impactor. You can calculate how much mass is delivered. And this is what Morbidelli did to do his 4.1 billion year thing. The issue is that argon-argon, which is used to date these craters, is underestimating the ages. So basically, we can take this point and move it to the right because of the argon loss that has happened, because argon is not retentive in these rocks. It is not a great way to date them. So we can move this to the right, but actually these error bars are also a little bit too small. Just as an aside, somebody compared, if I give everyone here an image of a crater on the moon and ask you to count how many craters there are and how big they are, you're all going to disagree. And so you can't just take one person's estimate for it and say that this is absolute, because in fact here this is now expressed as pixels on the image, for a crater that's 45 pixels across, there is something like, people are getting 200, counting 200 on a surface, or 50. So there's a huge disagreement here between various people, and these are experts who do this professionally. What you can see is that they're generally pretty self-consistent. Each symbol is a different expert, so the green stars are generally low. Those sort of upside-down blue triangles are generally high. So the relative ranking is okay, but it's the absolute number that is really tricky to get at. But you need the absolute number to estimate mass, which was this thing that if we just extrapolate it back, we get too much mass, so we need to lower it. So this isn't well constrained, so we have to take that into account. And the simple game that I wanted to play to show you what the minimum possible added uncertainty is to the ages is the following. People assign, right, here's a sample. Here again is how much argon has come out. This is that first argon. This is that last argon. This is the thing that's really hard to get out of your rock. You're doing this at like 1,000 degrees. You're practically melting your rock to do this. And the age comes up from 3.2 to 4 billion years. So they said, well, this last part here, we're just going to average this out and say it's 3.8. And what I said is, well, this is a lower limit, right? As you heat, you're going to lose argon. You're not going to gain it. You're just going to lose it as you heat your rock. So a better lower limit is 4 billion years, because that's the oldest actual heating step age that you got. So basically, there's 200 million years. This age is at least wrong by 200 million years, whereas in other cases, maybe it's much better. This is generally pretty flat at 4.2 billion years. So here, there's not so much of an issue, but in this sample, even though they're actually pretty similar samples, so in some there's this huge issue and in others there isn't. So let's just look at the Apollo 16 samples and say, what is this age difference between the age that the authors who did the work, wrote the paper claim, and what I think is a better estimate, this sort of oldest single heating step. And in one case, there's a 500 million year difference. So that's the difference in 500 million years is basically from today back to the Cambrian explosion. So that's, like missing between today and when there really was an advanced life on this planet. Just to give you a feeling for this, but most are, between 0 and 100 million years, but something like half have at least a 100 million year age issue. So, the next part is that there is some more evidence that this is not every lunar chronometer, not everything is as mobile as argon. Strontium is generally a little bit more retentive, and hafnium is really hard to lose. And the only point I want to make here is that the argon ages are generally younger than the rubidium strontium ages, which are generally younger than the lutetium hafnium ages. So the more retentive your system is, the older the age you tend to get. And so that's good, because it means that we're maybe onto something with these sort of analyses. So this plot is just to show you what actually happens to this really tight curve, right? What Morbidelli did is he drew a line through these data points and said, well, you know, we can extrapolate up, but if we take into account that the ages that are published on these samples are at least, you know, something like 100 million years too young, we can basically say, well, what's the probability distribution look like here? So these are basically fancy error bars. And so the yellow is where you're really sure. So we're pretty sure that, you know, something at 3.4 billion years would have this many craters per square kilometer on it. But up here, right, there's now a huge range. This could have been wrong by up to the age of, by 500 million years. There's a chance here. So basically, what this means is that in extrapolation, these curves that people are drawing through it to estimate the mass as they go back in time, right? So you go here, you go up, and you say, look, if this had been at the age of the moon, we'd expect 1 kilometer, or 1 crater per square kilometer. The surface would be totally covered. But as you actually go, the error bars are equally consistent with something like a factor of 10 lower. So we can then redo this extrapolation and say, well, what's the real uncertainty on this mass estimate, this mass delivered? And here it is. So basically, this is a log plot, mass delivered in kilograms, 10 to the 20th, you know, meaninglessly large numbers. But the main point is that here is the limit from the highly siderophile elements, this black line. And here is what this extrapolation from these curves gets you. So basically, these curves are running way too high in their extrapolation. They're delivering way too much mass by like a factor of 2 or 3 over what most of the simulations, right? The highest part, this is the number of simulations that I did, actually would predict masses that are right in line with what these estimates really are. So there's no need for this changing for this bombardment episode, because you can actually reconcile all of the evidence with a much simpler hypothesis that the impact flux is decreasing exponentially from the beginning of the solar system as you're cleaning stuff out, as everything is going away, and that what is happening is we're just, you know, we're just sort of underestimating our error bars, and that's why we're putting in these impact episodes, is that we're saying, you know, look, this is a hard limit, this curve gets us up here, how do we explain the difference in these curves? Well, we can just say, look, there was a huge change, and that this smooth extrapolation back in time doesn't work. Well, maybe it does. So then you want to look at the impact rates, and this is a plot that is a little bit tricky. This is now the impact rate per unit time. So this is the number of 20 kilometers that are 20 kilometers or larger per unit time. And here is this spike at 4.1 billion years, right? So here the solar system forms high impact rates. It declines, comes up, and then it continues to decline. And that this is where the planets are rearranging in their orbits. And so what I want to compare at is basically at 4.1 billion years, what is the impact rate sort of here versus here. So that's, the blue dot is this high impact rate, and the triangle is this low one here. And the point that I want to make is the simulations that meet the mass constraint from the previous slide, these gray dots, generally give you impact rates that are quite low, and they don't need to go up. So we don't actually need these impact rates that are capable of destroying the planet, right? That are going to, you know, cover the planet in 3 kilometer thick melt 6 times over, because this is probably just an artifact of some of the data and not taking into account the proper uncertainties that are happening. So can we actually do what we've been claiming to do, what came out of this Apollo program? And the answer for the timing is no. And the answer for the geochemical evidence is it's not unambiguous that you need it, because you can make this entire, you can meet all of these constraints with very simple, exponentially declining impact histories, in that if you look at this from a forward model, rather than trying to fit that data, you can generate data that looks really a lot like what we observed without doing anything fancy. So the issue with giving this presentation is that A, some of that was really technical, and B, the second part is that we just don't know a lot, because our sampling from the moon is simply not that great. We brought back 500 kilograms of rocks, but they were all loosely picked up on the surface of the moon. So basically, they picked up rocks that are sitting there on the surface, and so you don't really know where they came from. You don't know their history, and the thing is that I'm sort of hoping to come across is that people have been estimating this, and it's really fun to put really high numbers on this, that you have a late heavy bombardment, that you have this bombardment episode of 3.9 billion years, but that this is basically an over-interpretation of the evidence that we have in hand, and leads to conclusions that are geologically unreasonable because they contradict our record from this planet. And I think the record from this planet should be have a much more of a say than what the moon tells us about our planet, because it's precluding things like oceans back then, when we have really good evidence that we had liquid water on the surface of the Earth. And that basically these ages that we're dealing with are not from geochemically nice systems. It's not like uranium, lead, and zircon, which is basically the best system that you can data rock with. These are systems that are enormously tricky to use, and that the simplistic interpretations that people have applied to them go, those couple of bits of gas have the same age as each other, so I'm going to call that the age of my sample, is not actually a way forward to addressing this problem, and has probably led us astray since at least 1974, when this work was originally done. So basically, the punchline to this is that it doesn't look like, from the evidence that we have, that we need high impact rates to constrain anything, and high impact rates don't make any sense from the Earth, because we had liquid water and nice redox conditions. We have possible evidence for life back then, and things that look like plate tectonics, things that would have been destroyed in these impact rates. And so maybe we can reconcile all of this with much lower impact rates into the Earth-Moon system, and that we've simply overestimated them. So thank you. In the back.
Does the age spread correlate with the age spread of the authors of the papers?
Well, this is one of the really the parts that get a little more into the social side of how science is done. But a lot of this work was done by people who are either in the same group, or who are graduate students from the same group, or collaborators of the same group. So actually, there is not. And one of my main criticisms of this is that this is not something that is done where there's a lot of independent labs doing this with independent ways. Most of the argon evidence that's done was taken by the same maybe 5 or 6 people. And so this is a community that was basically left alone to do their work, and they hadn't, up until very recently, when the dynamical modelers such as Morbidelli or Bill Bodke got interested, because the computers were finally there that they could run these simulations, right? The Goins paper, 2005, is 30 years after this proposal. So the computing power took so long to catch up to where now they're able to run these models that when they look at this and say, well, people have dated this, this is a sort of a solved thing, we can take this as constraints to our models, and we can try and simulate this record, that basically we've run into this problem where what these models would predict the implications of this geologic record from the moon are completely absurd if you look back at the early Earth, because they would predict something that we don't have. So basically it's that for a long time, this was done in isolation, and it didn't really fit into the larger picture. And now that people are trying to bring it into the larger picture by using these dynamical models, that you end up with these very strange conclusions happening. So this is why now you can go back and look. And there's actually been a renewed interest in looking at some of these rocks from groups that have nothing to do and coming to very different conclusions than the original work that was done. So I'm not the only one. There was, for example, there's a group at Berkeley by Dave Schuster that has just done some phenomenal work along very similar lines, finding these same age complexities in these samples that undermine some of this interpretation. There's a group at Arizona State University that has, instead of dropping the rock in a furnace, they've shot lasers at it and heated very small portions at it, and they find very similar age spreads. That one sample is recording, different ages like 300 million years apart. So as different groups, as technologies move along, this is something that is going, in my view, a very interesting thing going forward, is trying to reanalyze these Apollo samples, especially from a much larger, from a group of people who historically have very little to do with the original work that was done here. Drastic changes to this might be coming down the pipeline as more people look.
Yeah, it's fine with Jupiter and Saturn, they changed orbits. With these giant planets, or many planet orbits for millions, billions of years, and all of a sudden you go, what caused that?
So this is the part that gets about the edge of my knowledge in this topic. I'm not a person that does these models are incredibly complicated, difficult to run. It is very expensive numerically to simulate this stuff. So there's a lot of things that are changed. So there's evidence. The trick with the Gomes model is that they managed to delay this instability. So the point is that when you form a solar system, it is very likely that some of your planetary orbits are unstable and will rearrange because where they accrete, they interact with each other. So basically, if you are in an orbit that has half of the orbital period of another body, you're interacting with each other. So if you go around twice, because they're always pulling on you at times in the orbit, so actually you're getting sort of pumped up and getting pulled in your orbit because of how you're relating to each other. Because the gravitational interaction of the one body on the other is lining up in the orbital period that you're sort of pulling on each other at very particular points in the orbit and kind of basically stretching it. You're driving up the eccentricity, which is how non-circular the orbit is. And the thing is, this happens a lot. We think that when planetary systems form, like within the first couple of million years, that this happens an awful lot. That planetary migration could actually explain things like hot Jupiters from the exoplanets. So that it's really hard to form something like Jupiter close to the host star. So the idea is that maybe there was some sort of migration, that there was this sort of resonance interaction that happened where the planets are pulling on each other in the orbit, but only at particular times to sort of, if I'm always pulling on you in one direction, even if I do it very little, you're eventually going to move. That this happens and that this could explain, for example, hot Jupiters, which we're finding a lot in the exoplanets. The trick for the early solar system is actually that they managed to delay that interaction until, by a couple hundred million years, because all of these things should have cleared themselves out really early. And there's some very recent work that suggests that those early numerical models were flawed because I showed you all the green dots in that movie, those little planetesimals. They're also going to interact with the planets gravitationally, right? And they're going to interact with each other gravitationally. In 2005, it wasn't computationally possible to consider that, so they turned it off. They said, these are really small objects, that can't be important. We'll not consider their gravity, so the only gravitational players in that simulation are the Sun and the 4 outer planets, so the 4 biggest planets. And recent models have gone back and run the same configuration that when you turn that off, gives you the delayed instability for, until 3.9 billion years ago, so hundreds of millions of years. And they find that when they simulate, because computers have gotten faster, all of those extra gravitational interactions that were left out, that the system blows up almost immediately. And these rearrangements, these orbital movements happen very quickly, which is what astronomically you would expect to happen. So it's possible that the Gomes et al. Explanation actually was a numerical artifact, based upon how they simplified the model rather than a viable feature.
Is that because of chaos theory, that little changes add up and boom, and then a big reaction occurs?
Yes, exactly.
use samples from the moon and possibly samples that have positions associated with them from the moon be of any help to help clarify this?
Absolutely. So one of the things is that the biggest impact crater on the moon is on the south side, it's South Pole Aiken. We don't think we have any samples from there. So what would be really great, and it's not going to happen, what would be really great is if we could fly there, drill into the we see where it's exposed, we have good arguments for this is the melt sheet from the South Pole Aiken impact, and what I'd really love somebody to do is to take a drill into it, grab a sample so that way you know where it's from. The current mission that's proposed to go there wants to grab loose rocks off the surface of the South Pole Aiken melt sheet, but that seems to be an enormously problematic thing because impacts can throw rocks around on the moon. So new samples would definitely help. They would definitely be able to answer some of these questions. The other thought that I've always had is the Apollo samples are all pretty close together on the near side of the moon. So if you connected the dots between the Apollo landing sites and kind of filled in that area, that's only about 4% of the moon's surface area. So that's really, really close. It's like sampling the Earth by just going to the United States. I think that is about right. So you're basically sampling a really tiny area. And what I would really like is for somebody to take a map of the backside of the far side of the moon, put it up, throw a dart, and send a mission there and pick up rocks. Right? We've made all of these great models that, if the 3.9 billion year spike is correct, we should be able to go to the backside, to the far side of the moon, pick up rocks, and they should support this hypothesis. So let's actually just make it a test. Again, probably not something somebody will do, which is send $1 billion spacecraft to a randomly picked site, because landing sites are picked through workshops and based off scientific interests rather than dart throwing. But that, I think, would be enormously useful is, let's go out, and we can't go back in time, right, to test our models, but let's go to the far side, let's go to a part of the moon we've never sampled and see if we see a clustering of ages of 3.9 billion years, or maybe this was local, maybe there's chronology issues, right? Before we make these grand conclusions, let's test our models. Well, thank you.